We'll start our third vodcast with an example of Archimedes Principle. I'm going to take a look at the mass of this white cylinder out of water. It's 1.2 newtons, or a little more than 120 grams. Next, what I'm going to do is I'm going to weigh the white cylinder while it's submerged in water. Now, the white cylinder is more dense than water, so when I submerge it in the water, it will sink and it will displace some water. I'm using an overflow can so that as soon as the cylinder hits the water, the extra water will be poured into a beaker. So I'm going to take just a moment here to let the water drain out and to lower the cylinder into the water. And you can see the weight, the apparent weight, changing as I lower the cylinder into the water. Wait just another moment for the water to drain so that I have equilibrium. And now I'm going to take another measurement. I'm going to weigh the cylinder again. When it's submerged, the cylinder weighs 0.2 newtons. Now that's a difference of 1 newton, or about 100 grams. There's 100 milliliters of water in the overflow beaker. Since the density of water is 1, that's about 100 grams of water. This illustrates Archimedes' principle. The buoyant force on the cylinder, which was 1 newton, is equal to the weight of the water displaced. I caught 100 grams of water in the overflow can, which corresponds to 1 newton.
If an object is weighed while suspended in a fluid, it appears to weigh less than it does in air due to the buoyant force acting on it. This apparent force, Fa, is equal to the net force acting on the object. For an object that is sinking or underwater, under the liquid, the apparent weight will equal the weight of the object minus the buoyant force. For a floating object, the net force will be 0 because the buoyant force will simply be holding up the object. We can combine all of these ideas of density and buoyancy together to determine the densities of unknown substances. And before we look at these formulas, it's important that we remind ourselves of something. It's important to remember that mass is equal to density times volume. And if I want to change mass to weight, then I would simply take density times volume and multiply that times weight as well. And what I'm going to do is take a ratio for a submerged object. So suppose we have a glass of water and a rock sitting at the bottom of the water. I'm going to take a ratio of the gravitational force to the buoyant force. And in this case, the buoyant force is less than the gravitational force. Here I've written my ratio of Fg and Fb. And now I'm going to make a substitution. Instead of writing the gravitational force, I'm going to substitute in density, volume, and g. And then the buoyant force, remember this buoyant force is equal to the weight of the fluid displaced. So the fluid pushed out of the way by this rock. So that is going to be equal to the density of the fluid times the volume of the rock times g. And when I cancel out the things that are the same, which is the volume and g, I end up with this formula, which says that the ratio of the weight of the object to the buoyant force is equal to the density of the object over the density of the fluid. For an object that's floating, we end up with this. We've got the density of the fluid over the density of the object is equal to the volume of the object over the volume of the fluid. Let's take a look at an example. A treasure hunter finds a coin that appears to be gold. He measures the weight of the coin and finds that it is 0.784 newtons. He then suspends the coin from a spring scale and weighs the coin while it is submerged in water. The apparent weight of the coin is 0.686 newtons. Find the density of the coin. Is it gold? And then the density of gold is given as 19.3 times 10 to the third kilograms per meter cubed. Okay, so what are we given here? We're given the weight of the object is 0.784 newtons. So here's our scenario. We're weighing the substance under liquid, under water in this case, and we've got that the gravitational force or the weight of the object is 0.784 newtons. Okay, now the apparent weight is 0.686 newtons. So the question is, what is this? What is the buoyant force? Well, the buoyant force is the difference between the force of gravity and the apparent weight. So there's our buoyant force. And now let's use the formula that we just learned about. We know that the weight of the object over the buoyant force equals the density of the object over the density of the fluid. So the weight of the object was 0.784. The buoyant force is 0.098. The density of the object is unknown, and the density of water is 1,000. And so we would cross multiply and solve this, and we end up with a density of the object of 8 times 10 to the third, or about 8,000 kilograms per meter cubed. And what we see is that this is nowhere near the density of gold, so this is not gold.
So I've made this video and I realize that I've made a mistake in my force diagram, and I've made a correction to it now using my video editing software. I did not include a third force, or I did not properly represent the forces. There's a buoyant force produced by the water that is displaced by the metal. And then there's an apparent weight. That's the scale. The scale is pulling up also. That's FA. And both of those forces together, FB, the buoyant force caused by the water, and FA, the apparent force, which is what the scale is providing, those, when you add them together, must equal the force of gravity. So for an object that is submerged and is denser than water, you will always have 3 forces, 2 up and 1 down.